Recording has started. So we were also discussing, communication models, and the last model was a time varying model. And at that time, I had some, electricity breakdown problem, so I was not able to show the relevant mathematics for a linear time variant filter, as you can see on the screen. So uh, this is its response or its output. This is additive white Gaussian noise. This is the impulse response, which is changing with time t. This is the signal. So they are being convolved. The signal is being convolved with an impulse response which is varying with t time. It is not fixed. And if we suppose that our response is something like this, so here also I will add that not only these amplitudes are time dependent, but these delays they are also changing with respect to time in a time varying channel, for example in wireless and acoustic channels. So, and once you put this value of this impulse response in this equation, the RT will come out to be this thing. So some of the steps were missing in the book, so that I have shown in my notes here. So this is the impulse response, this is the impulse response, this is the received signal. I just substitute the value of this impulse response inside this equation. This is the whole impulse response. Again the same signal, this is the noise. So now we can apply the famous shifting theorem, that the impulse exists only at the point of its existence. So all the functions that exist at that point, they will exist only at the point of the impulse. So impulse exists at tau is equal to tau k. Here I have also deliberately made the amplitude as well as the delay a function of time t, function of time t. Right. So the impulse exists only at when its argument is 0. All right. So all the other functions, this is not dependent on tau, so this will just come outside the integral. This tau will change to tau kt, the time varying delay, and then it will also come outside this integral because there is no tau now in this, in its argument, and in the integral we will just have delta 0, and we know the area under the delta is equal to 1. So hence you will get this as your receive signal, right? Same as is given in the book. In the book it is not dependent on time t. I have also showed it to be dependent on time t, so that you could arrive at a general model for these types of communication channels. If you have any questions, you can ask with respect to the previous lecture before we move forward. In the last lecture we had studied Fourier series. Just a review of your previous concepts, so that you are well versed with them before we go on to their application in the communication domain. Now we have the Fourier transform. So Fourier series are for periodic signals, but once you go from periodic to non-periodic signals, then these Fourier series coefficients, they are actually defined not only at the harmonics of the periodic signal, but they are defined for a range of frequencies. Will expand your signal in terms of Fourier in terms of exponentials or complex exponential coefficients, but you will see the spectrum will no longer be discrete, rather you have a continuous range of frequencies. And this is the famous Fourier transform, and this is its inverse. And again you have x of f, it could have its magnitude, it could have its phase, so it could be a complex number, it could be real also. It all depends on the time domain signal. You can also write it like this way or this way. In terms of omega you can also write. And x of t, the inverse is written as x of f e plus, and then you can write your x of f in terms of Fourier of x of tau, another variable. All right, so you could have, then you can combine them inside the integral. This could become e to 2 pi f t minus tau. And we also know from the famous shifting theorem that x of t can also be written as a convolution with an impulse. So you can compare these two equations. This shows us that the impulse could be written as the thing in the bracket. So an impulse comes out to be equal to this thing, or you can write, you can remove this minus tau from both the sides. So delta t comes out to be a summation of all the complex exponentials in the frequency domain. This means actually that the delta t function is actually consisting of all the frequency components in the frequency spectrum. Now the famous transform that would be needed, especially needed, others would also be needed, but some of them are important. Again, the famous rect function, and we all know that its Fourier is the sinc function, and I know by now you will have clear understanding of the sinc and the rect function. This is the rect function. So rect of t means its width is 1, starts from half, ends at half, and its corresponding sinc of f is a function that is going 0 at the integral values. Only at 0 it is 1, otherwise it is 0, and it makes this type of function. These are two very, very important functions in communications. Then we have the famous impulse function and the Fourier of the impulse. We just saw also previously that comes out to be 1. So it consists of all the frequencies in the frequency spectrum or the spectrum. Delta t consists of all the frequencies. All right, and you can also see, verify from here, delta t this exists at 0, this becomes e0, delta t integral becomes 1, ej0 becomes outside, is 1, so this output is 1. Vice versa, you can also see that if I take the inverse Fourier of delta of f, I will get a 1. This means that or you can say Fourier of 1 is equal to delta f. So what is 1? 1 is a DC signal. So a DC signal corresponds to a delta f, which exists which is a impulse which exists at f is equal to 0. So DC signal has an impulse here, and vice versa, an impulse in time is equal to a DC spectrum. Other you can also see by yourself, they will also be needed, but we will be just going through the important ones. Another thing, we know Fourier of x of t, x of t j 2 pi f t. I can write it as cos minus j. So I have two integrals, one with cos, one other with sine. And again, cos is even, and we know sine is odd. So they will also help us in decomposing or analyzing the Fourier transforms, as they helped us in analyzing the Fourier series coefficients. Now if I say that x of t is real, all right, so this means this is also real and this is also real. Okay, this is the real part of x of f, and this is times j. This is the imaginary part of x of f. So secondly, now we know cos is an even function, sine is a odd function. So the real part of x of f, so the real part is this thing. So real will go with an even, all right, and hence this means that the real part will be an even part. And the second thing is that the real signal goes with sine. Sine is an odd function. This means this is imaginary part. So imaginary part will be an odd function. And we know that if the real is even and the imaginary is odd, So this means you have a plus jb, and on the other side you have a minus jb. So this means that the Fourier series coefficients are Hermitian. You can see here that if you want to find the coefficient for some negative, let us say 100 Hertz, it will be equal to uh, the component at 100 Hertz. This is minus 100 Hertz at 100 Hertz will be equal to 100 Hertz time its conjugate. So if this is a plus jb, x minus f will come out to be a minus jb, but for real signals. And you can see all these properties. Real is equal to real, imaginary is the odd function minus imaginary. This means magnitude will be even, and this means that definitely phase will be odd. Now again, you can do some further analysis. If you say that x of t is not only real but it is also even, so even will go with even odd will go 0, so this will definitely go 0. So now the signal is x of t, which is even signal, but the Fourier series coefficients, they will also be even and they will be real, because the imaginary component has vanished or it has gone 0. So does uh, and so Fourier transform will be real and even. Vice versa, if I say that x of t is real and odd, so if it is odd, it will go with the odd function. So it will give, this will exist, but that with xt with cosine, that will go 0, because cosine is an even function, xt is an odd function. Odd even go 0. This means that the Fourier transform will definitely be odd, but it will be pure imaginary. It will be imaginary and odd. So this comes the definition of signal bandwidth. Again, I have told you, in the beginning of the lectures about this important concept. Again, this is repeated here. That is a range of the positive frequency. Range of the positive frequencies. We do not include the negative frequencies in the bandwidth. All right. We only include the positive frequency. So maximum positive frequency minus the minimum positive frequency will give you the bandwidth. Other concept of duality, this is also very much used. So just a revision, if I say this is a Fourier transform of x of t, then this comes here and this comes here. So I can say that the frequency spectrum of this x of t will be equal to Fourier of its x of minus t. All right. This could also be x of minus f is equal to Fourier of x of t. So minus could go here or on this side or on this. This can happen on both the sides. But the main thing which is to be understood is that the Fourier transform pairs are dual. So this is the frequency spectrum of this time domain signal. Then this time domain signal will become, if it becomes a frequency spectrum, then its time domain signal will be the previous frequency spectrum of its corresponding time domain signal, with just putting a sign of negative, or either on this side or on this side. So this gives us a very famous transform. We have seen previously that a rect gives a sinc. So what will a sinc give us? What will be the Fourier of the sinc in time? It will give us a rect, but rect with respect to minus f, and rectangle minus f, rect is a even function. So rect of minus f will definitely be giving me rect of f. So now we also know the Fourier of sinc of t, as we have known the Fourier of rect of t. And this is also shifting in time domain. So this you also know that if I shift in time domain, it means that I am multiplying my Fourier by a complex exponential whose phase is eg2 by f t naught, which is determined by that shift t naught. So If I have a rect function shifted by this thing, so this will be equal to sinc of f multiplied by e minus j2 by f t naught 3/2. So f t naught, in this case यहाँ पे sinc of f की गलती होगी, you can put a sinc of f here, but the answer is right. Another important thing, especially this will be used in sampling or digitization, is the impulse train. All right. So first of all, I just find the Fourier of shifted impulse. So I know this will be the Fourier of impulse, which is 1 times e minus j2 pi f n t naught. All right. But Fourier of impulse is 1, so I guess this thing. If I make its train, Fourier of the train will be just train of these complex exponentials. All right. Now we also know that this is also a periodic signal because these trains are being repeated, or these impulses are in this train, the impulse is being repeated after every t naught time. So this is a periodic signal. We have seen previously that the Fourier series coefficients of this periodic signal comes out to be this thing. This is the Fourier series coefficient, and this is the the rest of the Fourier series coefficients going from infinity to infinity. ej2 pi the n f naught. So this is n over t naught t. So this equation can also be written as follows, like this. This train can also be written like this. So in this same equation, if I just these are just values, so I can very well alter them. I can replace this t by f and this t naught by 1 over t naught. So this will become 1 over t naught. This t becomes f, and here I also make similar changes. This t naught is replaced by 1 over t naught. This becomes t naught. This becomes t naught, and this becomes f. So I can also interchange the variables. Infinity to infinity, I can write this from again from infinity to infinity, but with the minus f sign. It won't make any difference because you are going from infinity to infinity. So you can also write it as follows. So this is one representation, and so I can finally write that this summation is equal to this train 1 over t naught. So I have found the representation of this summation as a train in frequency, and you could see that this summation was occurring here. So I can write the Fourier series of this train as this train. Fourier series of this train is equal to this train. So you can see this is a train in time, and its corresponding train and its corresponding Fourier is also a train in frequency. All right. So if you, let us say, if you say t naught is 1, just shifting by integer multiples, so you will get a train in time corresponding t naught is 1. So this 1 over 1 goes away, corresponding to a train in frequency. Train in time is train in frequency. Also an important relationship will be used very much. So if you multiply in time by a, this a could be division or multiply, whatever, but you have just put a constant with t, so that constant will go in frequency as 1 over a and amplitude as 1 over a mod. So this could be, this a could be anything. It could be t over a, but in that case it could be t over b. In that case a will be equal to 1 over b. So 1 over b here and 1 over b here. Okay. Whatever, you just have to see whatever is the term with which t is being multiplied. It could be 0.4, it could be 2.4, whatever, and you will have the corresponding frequency spectrum like this. In this contraction or expansion and all that. So again we have a pulse, its height is 3, and it is now extending from 0 to 4. So we have a rect whose width is 1, but now its width is 4. This means that this rect has been expanded by 4. Alright, that is why there is a 4 dividing it. Now if it was not shifted, then it would have gone from -2 to +2, but it is actually going from 0 to 4. This means there is a shift of 2 also towards the right hand side. That is why it is t minus 2 over 4. So I take the Fourier of this term. So 3 comes out, then -2. For -2, how do we represent it? We represent it as e minus j 2 pi f times t naught. So t naught is 2, this becomes 4.
सर
We
ये
have
माइनस
just
टू
Fourier.
क्या है?
Yes, if you have any question, you can ask. What you're saying? Please
सर
repeat your question.
ये -2 कैसे आया है? आपने क्या कहा है अभी?
All right. Again, a problem is that, let us say if there was no -2, in that case this would have been a rect t over 4. All right. So what is the meaning of this signal? The rect signal has been expanded by 4. But what is the rect signal? If you could just see, the rect signal was extending from -half. This was the rect signal. The actual rect of t is like this. If I divide it by 4, expand by 4, then what will happen? This will be going from, its total width will become 4. So it will be starting from -2 and it will be ending at +2. So its width would have been 4. But my signal is not starting from -2 to +2. It is starting from 0 to 4. This means I need to shift my rect from -2 to 0. This means that I have to make a shift of -2 on the right side. I have to shift this, I have to delay this. That is why there will be a -2.
Okay, sir, I got you.
All right. Now if I take its Fourier, so -2, I take this phase out. This becomes ej 2 pi f t naught. So t naught is 2. This comes here. Then I have this thing, rect t over 4, and now we apply the theorem. This means I am multiplying my t by 1 over 4. This means it will give me a sink f divided by 1 over 4. Divided by 1 over 4, this 4 will go in the numerator, 4 of f. And similarly, the amplitude will be 3 over 1 over 4 mod. This 4 will go in the numerator, this will make it 12. Alright, I hope all of you are understanding. Convolution is very famous, you all know this, so you don't have to go through it. Yes, convolution in time means product in frequency, and you can find very important functions by the help of this convolution property. So if I am convolving two rects, I get a triangle. All right, convolution of two rectangles, that gives you a triangle. And what will be its Fourier? It will be just multiplication of the Fourier transform of the two rects. Each rect is sinc of f, it will be sinc square of f. Similarly, you can also apply this thing here. This is a rect, but t over 4. This means that you are multiplying by 1 over 4, so sinc of f over 1 over 4 sinc 4f into 4. And this is rect of t, but rect of t is sinc square of f. So rect of t over 2 means you are dividing by 2. This means you are multiplying by 1 over 2. So this means you will multiply this by f 1 over 2. This means 2f. And this 2 will also go in the magnitude. So this will be the Fourier. Another thing is modulation. So what is modulation? That you multiply your signal by a exponential, and actually this is a high frequency. Most of the time it is mostly a high frequency exponential. So it gives you xf minus xf naught. So multiplication by an exponential shifts the frequency from x of f to x of f minus f naught. The whole spectrum shifts to f naught. Again, a very good example. So if I take x of t, so what is the Fourier transform of ej 2 pi f naught t? So I will take the Fourier transform of ej 2 pi f naught t. So I can just say it is a Fourier transform of 1 times ej 2 pi f naught t. But I know the Fourier transform of 1 is actually delta of f. 1 is a DC signal, its Fourier is delta of f. Multiplying with ej 2 pi f t means I'm shifting my delta f to f naught. Alright, this becomes delta f minus f naught. Similarly, the same thing you can apply here, because cosine can be written as ej omega t and e minus j, in other words ej 2 pi f naught and e minus j 2 pi. And you can see that ej 2 pi f naught t, this will give me del f minus f naught, as we saw here. And this thing e minus j 2 pi f naught t, this will give me delta f plus f naught. Alright, this will be the advanced version in the negative frequency. This will exist at f is equal to minus f naught, or this will be the delayed version. This will exist at f is equal to plus f naught. And if you want to multiply the signal by a cosine, this means you have multiplied the signal by ej and you have multiplied the signal by e minus j. So this will shift the spectrum to minus f naught. But this now not delta f, instead of delta you have x of f. And this will shift the spectrum of x of f to plus f naught. This will be plus f naught. So you can see all these examples. You have cos pi f t, but it is restricted from minus half to plus half. This means cos pi t is being multiplied by a rect function in time. So we can apply the property that I am multiplying my rect by cos, and I know cos is what? Cos is ej plus or e plus j, my you know what, that 2 pi f naught. So in that case, you know, my f naught is 1 over 2, so that is why 2 cancels. So 2 pi f t becomes actually pi t. So you know your f naught is actually half. So you will shift the spectrum of a rect at minus half and at plus half. So you know rect is sinc, so sinc at half, minus half, and sinc at plus half. Another important relation is a very famous Parseval's relation. So as we saw for the Fourier series, you have the the Rayleigh theorem. Here you have the Parseval's relationship. Also, sorry, it's also called the Rayleigh theorem, and you can see here that x of t y conjugate gives us x of f. This product is same, it can be proven. Or if I say yt is x of t, so x of t conjugate becomes x of t mod square is equal to x of f mod square. So this means if I say this is a, let us say, for an energy type signal, so this is power integrated, this becomes energy. So energy in time is equal to energy in frequency. This is also called the Rayleigh theorem, and it is similar to the Parseval's relation for periodic signals. Energy use. Now another famous thing that you have to understand is the autocorrelation function. Okay, so autocorrelation function is defined as follows. So it is a little bit different as with respect to convolution. So here you could see that r of tau is actually x of t minus tau d of t. You just shift the signal by tau and then multiply them from infinity to infinity. Take the product, you will get one answer for one value of tau. For various values of tau, you will get a whole function. So that is why it is a function of tau, function of delay. It is different from the convolution function, because in convolution, this was, if I am taking x of tau here, so between two functions, so this would be a dummy variable, and then this was x of tau. If this was xt convolve with xt, then this would be x of tau, x of t minus tau for convolution. But I will also tell this in my notes because some of the steps are missing. So it can be shown that the Fourier of this is equal to this thing. So this is again absent from the book, which I will show. And it can also be shown that the autocorrelation is equal to convolution of these two functions. And then by applying the Fourier of convolution, you can get a proof of this. And we will be showing this proof in a while. But one important thing is that if the Fourier of the autocorrelation is always xf mod square, this means that whether xf is complex or non-complex or real, xf mod square, xf mod is a real number and mod square is also a real number. So this means that its Fourier of the autocorrelation function is always a positive function, real valued positive function. So as some of the steps are missing, I would like to go into its mathematics. So you can see that autocorrelation is defined as follows. Tau, this is x of t small, x of t minus tau d of t. Alright. But we know what is convolution. Convolution of a function with itself will be x of tau, x of t minus tau d of tau. So you can see the dissimilarity between these two. Right. First of all, you have a conjugate, and this is t minus tau but with d tau, while this is also t minus tau but with dt. It's the difference. Let's try to make up this difference. First of all, I write the convolution equation, but with the change of variables. From x of t I go to x of tau. Alright, you can make any change of variables. So x of tau convolved with x of tau is cx of tau, and this tau I have changed to t. Alright, because here tau is a dummy variable, now t is a dummy variable, and this t has been changed to tau. Alright, so this t has been changed to tau, and rest of taus, they are all t's. Just change the variables. Alright, so this is also convolution, because you have a function and then it's flipping or its reversal over the vertical axis, minus t, and then plus tau means its delay by tau. Same convolution, no change. But now I make another change. I say no. First of all, I take the conjugate of the second function. So if I take the conjugate of this function, this means the second function is conjugated. Is conjugate. When I say no, I also time reversal or flipping of the vertical axis. The second function is also flipped with respect to its tau. So if it is flipped here, then this means that it's t. This is the delay and this is the dependence. This delay will dependence on t will also be flipped. So instead of minus tau, when it will be put inside the convolution integral, it will be flipped again. This will become plus tau, or plus t, because now t is a dummy variable. This will become plus t. And previously, for minus t, if you want to delay, you have to put plus tau. But for plus t, if you want to put a delay, you have to put minus tau. Okay, so minus tau is the delay now, and this is plus t. Now this is the exact definition of the convolution function. This this right hand side is the exact definition of the autocorrelation function. So right hand side are same. I can equalize the right hand side, hence I can also equalize the left hand side. So the convolution has been proven, the autocorrelation has been proven to be the convolution of the same function but with flipping and conjugation. Now I can take the Fourier of Rx of tau. So x of tau will be x of f. X of conjugate will be x of conjugate minus f, and then x of conjugate minus tau will be equal to x of conjugate f. Hence I can say that the convolution of x of tau is x of tau conjugate is actually nothing but this is conjugate conjugation. This will be multiplication in the frequency domain x of f with x conjugate of f, and this becomes x f mod square. Hence the Fourier of the autocorrelation function is actually x of f mod square.
सर सर आप कैम स्कैनर फाइल हमारे साथ शेयर कर सकते हैं?
हाँ जी जी बिल्कुल, ये आपके ना उसमें लग देंगे हम लोग, और जो आपका फाइल्स वाला फोल्डर है जनरल वाले फोल्डर में रखा होगा सारा, इंशाल्लाह मैं ये डाल दूंगा।
ओके,
तो आप
थैंक यू
वही
सर।
ये नोट्स आप अपने पास डाउनलोड भी कर सकते हैं। वीडियोस आप सिर्फ वॉच कर सकते हैं, वो मगर डाउनलोड नहीं कर सकेंगे। वो मैं वीडियोस को उसमें प्लेस करूंगा क्लास मटेरियल्स में, जैसे मैंने ईएमटी में किया था, मगर नोट्स जैसे ईएमटी में अवेलेबल थे ये भी आपको अवेलेबल होंगे। Let's go first of all to the book back. So we have explained all of this which was missing. So differentiation property you have also studied, so I won't go into detail of these things. You can read up by yourself as you have studied this in your previous course. I think 2 times you have studied all of this, so this can be left, but this is no more needed. Now, transmission over LTI system, so you know it is very simple. If you have an LTI system, the output will be convolution in time, and this means that in frequency it will be just simple multiplication. And so if I say that I have x and h, so what will be my y? Y will be just multiplication of these two rectangles. Okay? Whatever is shorter will determine the overall response. So you can see all of this here. And high pass, low pass, you all know that. So we don't have to go into detail of these things. FII you will be studying in mashallah in your DSP, so that will not be covered for this course. Now, this is a very important topic, power and energy. I know you know what is a power and energy signal, but they need to be revised with respect to their autocorrelations, their power spectral densities, their energy spectral densities. They need to be revised here. That is why I am giving them importance here. So we all know what is a power signal, what is energy signal. Energy signal whose energy is finite. Okay. So for them we define energy as follows. So energy will be xt mod square will become its power. Alright, V square. All that which I was telling you, it is written here. Power delivered to a 1 volt 1 volt 1 ohm resistor, so it will be V, but the power is V square over R, the V square over 1, the V square is the power. So x of t, let us say, is voltage function, so this will come out to be power V square over R is 1, this is power. If I integrate power over time, I will get energy. So in this way I can find the energy of an energy type signal. Provided it is finite, it is energy type signal, I will get the energy. But many signals, they don't have finite energy. For example, the periodic signals, they are going from infinity to infinity. For them, what we do, we again have the instantaneous power, we integrate them over time t, okay? But then we divide them by time t, so that we have power, it becomes energy, then dividing by t, it will become a power, but average power. Alright, so this will be used for those signals which are power signals, because if they are energy signals, then this will be totally zero, because this integral will be finite over infinity will be zero. So it will only define for power signals whose energy is infinite but their power is finite. And let us say this is some infinite signal, but if I have a periodic signal which is also infinite, so you will be seeing you can just shorten the time. Again, you will just integrate over one time period, but you just have to divide by the time period itself. Okay? But this formula actually boils down to this formula for periodic signal, but in general this formula is for periodic or non-periodic power signals. So we have energy type signals. We define the autocorrelation as follows, just as I showed you in my slides. It could also be, written as for this, I just showed you, no problem. But you can also write it as follows here, that you uh, put plus tau here, this tau tau cancels, and you have x of t plus tau x conjugate of t. Both are the same equations. Now in this equation, you can very well see if I put tau 0, this will become x of t into x of conjugate of t, this will become xt mod square. And we know what is xt mod square, this is the power integrated with time, this becomes energy. Hence, energy of a power signal, of a energy signal can be found by autocorrelation 0. And this is autocorrelation 0. Because if you put 0, then this becomes x of t into x conjugate of t, or xt mod square. So autocorrelation 0 gives you the energy of the signal. This I showed you in my slides, that the Fourier of this is xf mod square. So this way I have also proven. And you can also see that if energy is, xt mod square, it can also be written xf mod square df. This can be you can use the Rayleigh theorem as we just studied previously, but you can also use the Fourier transform result, because you know that the autocorrelation is inverse Fourier of xf mod square. We have just proven here from this test. But if I put tau 0, this becomes this 0, this ej0 is 1. Hence energy is also equal to xf mod square df. Or this is, autocorrelation is 0, but autocorrelation 0 is equal to energy of the signal is also equal to xf mod square df. So you can see the energy is yes equal to xt mod square, but it is also equal to xf mod square. So for example, देखिए ना, this is a very good advantageous point. If you have a sink in time, and if you try to find this energy, it will become very difficult, because sink square and then integral, you have to integrate from infinity to infinity. But you know that its Fourier is just a rectangle, so its energy can be easily found by just taking its mod square. You will just find the energy. So you can switch between frequency and time to find the energy of a signal, and hence you will be able to find compactor expression in the other domain to get a value of the energy. The output we all know is convolution, or in frequency it is just multiplication. So if I want to find the energy of the output, it will be yt mod square, or you can also write it as yff mod square, just see, which will be equal to ry0. But what is yff? Yff is equal to xf into hff. So yff mod square will be xf mod square into hff mod square. Very simple. Alright. You can also write it like this. All these things are the same. And you can also see that output autocorrelation can be written as convolution of the input autocorrelation with the autocorrelation of the impulse response convolved with the autocorrelation of the input signal, because xff mod square inverse Fourier will be autocorrelation of x. hff mod square will be Fourier inverse will be autocorrelation of the impulse response. So their convolution will give you the output autocorrelation. Convolution of the autocorrelation of the individuals will give you the autocorrelation of the output. So if I say that HFF is just 1 for a very small range of frequencies of delta W, then you can see YFF will be just XFF, because HFF is 1. You will only see for that small range of delta W frequencies. And again, EY is this thing, energy. Just summing YF mod square, you will get the energy as we have just seen earlier. But this will be as equal to XF mod square times delta W. For that delta W, you just have this x of W. So y of f, this whole integral will give you the area under the curve of y of f mod square, which is actually y of f is equal to x of f times the width of the window, which is delta W. So the output energy, EY is the energy, represents the energy located around f is equal to W of delta W bandwidth. This is the amount of energy. Okay. So we can say that x2W is actually the energy divided by delta W. So x W mod square will be energy, total energy divided by delta W. So what this means, I am taking the energy per bandwidth. This energy per frequency, or you can say this is energy spectral density. Energy per frequency. Alright. Energy per unit bandwidth. This is why it is called the energy spectral density or the energy spectrum. It is equal to x of f. Another word is the Fourier of the autocorrelation of x. Again, for energy signals, this is the autocorrelation. The Fourier is x of f mod square. If you want to find the energy, just put Rx0 and you will get the energy, which is x of f mod square df, or x of mod square is equal to gxf, and you can just integrate this same thing. If you pass it to a filter, the output will be convolution of the autocorrelations, or the output will be the convolution of the input as has happened in an LTI system, and the output spectrum will be the input spectrum and the impulse response spectrum, or x of mod square into h of f mod square. Now, then we have power type signals. What are power types? We all know that their energy is zero, but their power is finite. So for them, we define a different type of autocorrelation function. So their autocorrelation function is the same thing, but 1 over t goes to infinity. That is the change. Because we have to do that. Otherwise, if we do not do this 1 over t, this and this t goes to infinity, this will go to infinity. Because this will give you the energy of the energy spectral density. But we want a power spectral density. That is why we take the energy, because if tau 0, this becomes xt mod square. The integral of time, this becomes energy divided by t, this becomes power. So because you know that power is finite, that is why we define an time average autocorrelation function. I think all of you have studied the autocorrelation of a power type signal in your previous class. Have you studied autocorrelation of a power type signal?
सर
No,
याद
sir.
नो
नहीं है.
सर, नहीं पढ़ा था.
नो सर.
चलो ठीक है. पता नहीं, मुझे तो शायद वो बता रहे थे कि आप लोगों ने ये भी पढ़ा हुआ है. तो मैंने कहा मैं फिर भी रिवाइज करवा दूं, बाद में एकदम से जब मैथ आएगी फिर आप कंफ्यूज ना हो जाए.
सर आप करवा दें.
हाँ, इसलिए
सर आप करवा देंगे.
राइट, ठीक है. Alright. So you could see here that this is the autocorrelation of a power type signal. We definitely make it power so that we get a finite number. So again, if I put tau 0, this becomes x of t into x of t conjugate. This becomes x of t mod square. And this will become Rx0, because tau is 0, this will become Rx0. And you can see that power is equal to autocorrelation function at 0. But remember, if autocorrelation of energy signal, then autocorrelation 0 gives you energy. But autocorrelation of a power signal, then autocorrelation 0 gives you power. This is the difference that you must always keep in mind. So again, as in similarity, the development of energy spectral density with the autocorrelation of energy signal, we would define another term which is called power spectral density, which is the Fourier of the autocorrelation signal for a power signal. That was autocorrelation for energy, it was giving you ESD, energy spectral density. This is autocorrelation for power signal, it will give you PSD. And if this is the Fourier of this is this means that, as I've told you, Rx0 will be equal to Fourier of this, and EJ0 is 1, so this, Rx0 will just give me Sx of f. So once I will be summing this up, now I will get my power Rx0. Alright, so power will be Rx0. For 0, this means EJ0, this becomes S of xf. So if I sum over the Fourier of the autocorrelation, I will be getting the power. Previously, I was getting the energy. Same thing as I have told you will happen here. That 0 will correspond to this thing or this thing, xf and xft, so they both are equal. But this was done for energy, but you can also do this for power. All right. All right. Now again, what will happen if I pass it to an impulse response? So this is the output. Convolve, you all know that. Autocorrelation of convolve will be given as follows. And then I can do some, manipulations. I can write these two as convolutions, respective convolutions. I can do change of variables. T minus U is equal to W. So I'm actually changing T to W, keeping U constant. So instead of dt, I will get dw. The limits will go, t was going from minus t to plus t. So now w will go from minus t over 2 minus u to plus t over 2 minus u. There is a mistake here, this will be minus u. So you can correct this, this is minus u, this is not plus u. And again, actually, you can see this is also a very important step. Actually, one problem was also, I was thinking of giving you an electromagnetics final, but I didn't give it because it was just like this problem. So you had one differential and that differential was coming in the integral. So I wanted to give this problem, but I realized that students will get confused.
सर आपका माइक ऑफ हो गया है.
ये किसने मुझे म्यूट कर दिया? अच्छा, can you now all hear me?
Yes, sir.
Someone muted me. I don't know how it's muted. It's quite unusual. All right. So which point I was at? From which point you were not hearing me?
सर आप EMT का फाइनल बता रहे थे कुछ.
Yes. So I was actually telling you that in this problem you could actually see that you have a differential here, and that differential is also coming inside the integrals. So there was one problem in the end problems where this was also happening. If you could see, you had a transmission line and you need to find the inductance of a transmission line in a circle. So for finding the flux linkage, you had to integrate over a circle. For the circle, you were getting some type, the limits of x or y, they were coming in here. At the same time, you were taking dx and dy. So I realized it would be problematic to students because they might not have done or practiced such type of integrals. But these types of integrals do exist, both in signal systems approach as well as in electromagnetic or high frequency implementation of circuits, as well as signal processing. And this could happen that you have a differential as well as that differential is existing inside the integral. So there is one mistake here. You can just put minus u, so this will be all correct. So this thing can be written as autocorrelation. WW and then u minus tau minus v. It will be w actually minus bracket tau plus v minus u, that will come here. All right, because we have x of t minus tau is a minus tau. So this total tau comes here, which is this thing. This is also right. Then you can write this with this as convolution. All right. And then this can also be written as convolution. So the output autocorrelation is actually the convolution of the input autocorrelation with the impulse response, and the impulse response convolved with the impulse function. But you can also see that h of t convolved with h conjugate of minus tau. H of tau convolved with h conjugate. What is this? This is also autocorrelation of h. The same thing. But remember, these autocorrelations are defined for power signal. Similarly, they were defined for energy signals. But this is autocorrelation and this is autocorrelation. Autocorrelation of x, autocorrelation of h gives you autocorrelation of y. And again, you can take the Fourier. This will give you, Fourier of autocorrelation is as previously s of xf dsd. This is simply h of f. This is h of f conjugate, and hence this becomes hf mod square into s of x. So the output spectral density is equal to the input spectral density times hf mod square. This is very important. Times hf mod square. The filter response is doubled, is squared. All right. And again, you can read this up. This means it is telling you all that this gives us the power spectral density. All right. Because you are divided by 1 over t, this will definitely give you power spectral density. And this is a simple simplification. We know autocorrelation for power signal is given as follows. But if I say that my x of t is periodic, I can write my integration as like this. From over one time period, and that time period is 1, but I am extending it to multiple time periods. It is going from infinity to infinity. That infinity goes in with respect to k, not with respect to t. These two integrals are the same. So then this, could be written as k times, because, one periodic function is repeating again and again. So its autocorrelation of one period will be equal to others. They can just write k multiple of its autocorrelation. And then kk cancels and you have this thing. So for periodic signal, you can write autocorrelation also as follows. But again, you can see this will be giving you power. This is power integrated, this becomes energy, then divide by T naught, this becomes the average energy or power. Or you can say also, this is autocorrelation, but this is time average autocorrelation. For energy signal, you don't have 1 over T naught, that is why it was autocorrelation. For periodic signals, you can also substitute the Fourier series coefficients. the famous Fourier series coefficients of these two terms, it will become like this. The Fourier series coefficient of x of t. Now ej2 pi, it is actually n f naught or n over t naught, but you can write m for one, and for the other you can write n minus m. इससे यहाँ पे थोड़ी सी गलती भी हो गई थोड़ा, इधर भी यहाँ इसने m डाल दिए, यहाँ भी m डाल दिया, हालांकि वो एक ही m आना था. We had made a mistake here. So there are mistakes in the book. Actually, you know, if you see the Fourier series coefficients, so you could see that x of t is this thing, and yes, its conjugate is this. All right. X of t. Yes, this is very right, but so you can also write the autocorrelation if you apply the Fourier series coefficients as x of n mod square with respect to the Fourier series exponentials. Because you know that they will just exist at the point where n is equal to m. At all other points, this will be just equal to delta. Only at m, this we also saw previously. They will only exist at the point where m is equal to n. So this will be just x of n into x of n. This will become x of n mod square. And hence you will be having these two things, x of n mod square. Only the same terms will be there, other terms will be zeroed out. So autocorrelation for a periodic signal can be written as follows. And then you can just take its Fourier, and you know this is just a constant, and the Fourier of the exponentials we have just seen. Fourier of exponential, it is just, you know, this is a train of the, you can just say this is ej2 pi f periodic f, repeating at f naught, n f naught, then 1 f naught, 2 f naught, 3 f naught. And this can be represented as a train in frequency. We have just also seen this previously also. If you can take its Fourier, you will get this delta f, and as you have a summation, you will get its train like this, repeating at 1 over t naught in frequency. All right. And you can integrate this, this will be the total power. This is just summation of xn mod square. total power we have also seen, it comes out to be the frequency spectrum of the impulse response, frequency spectrum of the signal, of that periodic signal, and you just have to multiply them, you will get this thing, and then the total power will be just sum of these two terms, and they will just exist at these points n over t naught. So you will get the total power to be, you can integrate this over all the frequencies, integration delta will cancel, and you will just get this sum as the output power. Hilbert transform we don't have to basically do now. This we will be doing once we will be doing the other chapters, and we'll come back and study it. So we can go to the low pass and the band pass signals. So low pass signal is a signal which is around the zero frequency, as I just showed you. Rect of t, or if I say rect of f will be around zero. It will be a low pass signal, right? Many times you can say it is a baseband signal. It consists of negative and positive frequencies. What I am saying is a real signal, and a real signal, has energy, has a signal has minus negative frequencies and positive frequencies. I'm just talking about from 0 to 3K. So I am speaking a baseband signal or a low pass signal. All right. I have negative and positive frequencies. But let us say if I modulate my signal, I shift my signal to some AM radio station, to some FM radio station, or let us say to some mobile. Okay. So my spectrum will go to 1 gigahertz, maybe to 1000 kilohertz for AM, and for FM it will going to 100 FM or FM 100 megahertz. So my frequency components, which were just let us say, if they were real, they were symmetric from minus 3 kilohertz to plus 3 kilohertz, they are now extending, they are now transported, or they are now shifted to 100 megahertz minus 3 kilohertz and 100 megahertz plus 3 kilohertz for a FM signal, or let us say modulated for let us say for the FM band. All right. So I am speaking a low pass signal, and once it is modulated, it becomes a band pass signal where the spectrum is far away from the zero frequency. So what happens? The negative frequency, they also become positive. All right. And this shift by FC is
सर आप पिछली बात समझ नहीं आई, फिर से बता दें।
आपको क्या बात नहीं समझ आई?
सर अभी आप जो बताया था ये जीरो फ्रीक्वेंसी वाला
हाँ, लेकिन what I am speaking right now, sound signals mostly they go from most of the amplitude of these frequencies, they go from 0 to 3 kilohertz. All right. But remember, I am speaking a real signal. So, my spectrum will be conjugate symmetric, as we have just studied. So it is conjugate symmetric. This means my frequencies are extending from minus 3 kilohertz to plus 3 kilohertz. All right. So I am speaking a signal which is around zero frequency, occupying negative and positive frequencies. So this is a low pass. This is a baseband signal whose content is around zero frequency. But if I modulate my signal to some carrier FC, all right, you just multiply your signal by EJ2 pi FCT. So your spectrum will now shift to FC. Let's say 100 megahertz. So your same signal will now exist around 100 megahertz. 100 megahertz minus 3 kilohertz it will start, and 100 megahertz plus 3 kilohertz it will end. So that it will now become a band pass signal. All the negative frequencies will now become positive because you have modulated it with a frequency FC which is much greater than the bandwidth. Remember, when your signal was low pass, your bandwidth was 3 kilohertz. But when your same signal becomes band pass, your bandwidth becomes 6 kilohertz because your negative frequencies have also become positive. Ari, have you understood? This same student who has asked this question?
Yes, sir.
if you have any questions, you can ask, because I will be ending the lecture in 5 minutes. Okay, this is the last topic from this chapter which we will study, and then we will move on to chapter 3, the next chapter, which will be amplitude modulation. So this is also just a revision. Maybe many of the students have studied this band pass and low pass. So if not, then just bear with me. In 2-3 minutes, we'll just cover this up. Now, what is the extreme case of a band pass signal? It is a signal whose frequency is equal to FC, or we can say its bandwidth is 0. It is this thing, the famous cos signal. All right. You know, the cos signal has 2 EJs. One EJ will be at positive FC, another will be at negative FC. But the positive FC is just standing at positive FC. It has no bandwidth around it. The set, what is bandwidth? Highest positive frequency minus highest positive frequency. It is FC minus FC, it is 0. It is 0 bandwidth signal. Now, I can also represent these signals by the help of a phasor. First of all, let us say what is a phasor. You know, phasor is a representation of a complex number having its magnitude and its phase. Okay, you know, phase can come 0 to 2 pi, minus pi to pi, whatever. You all know this, so you don't have to repeat this. And this is the, you know, phasor diagram. So a complex number can be represented as an amplitude and a phase. All right, A EJ theta. So what we do, we say, all right, this phasor's theta is actually revolving with the frequency of WC, which is 2 pi FC. So we just multiply our AEJ theta with EJ2 pi FCT, and the result will be AEJ2 pi FCT plus theta. So you have your AEJ theta, but it is multiplied with EAG2 pi FCT. So previously your AEJ theta was just standing. Now once you have multiplied with EAJ2 pi FCT, so what is this 2J pi FCT? With respect to t time, your phase is moving from 0 to 2 pi. And again, it is going from 0 to 2 pi. So it is just like a moving vector. And if, let us say, FC is positive, it is just like you are moving positive phi's, or in other words, you know, you are moving counterclockwise with a speed controlled by the angular frequency 2 pi FC or by FC. And the projection of this EJ2 pi FC on the real axis will be A cos. Imaginary axis, this will be A sine. All right. And you can, the signal same. You can apply the, you know, cosine identity, cos alpha plus beta. You can write it also as follows, this thing. And you can say that A cos theta is XC and A sin theta is XX. A cos theta and A sin theta are just the real and imaginary part of AEJ theta. AEJ theta will be equal to A cos theta and A sin theta in the real and the imaginary axis. All right. So this single frequency, 2 pi FC was a single frequency, 0 bandwidth, has 2 components. One component is along cos, other component is along, this is called the in-phase component along the cos, and this is called the quadrature component along the sine, because they are along orthogonal components, cos and sine. So why cos and sine, they are orthogonal? Because, you know, if you just multiply cos with sine, integrate over the time period, we all know even an odd function, this comes out to be 0. That is why they are orthogonal. That is why they are called quadrature 90, or orthogonal component, in phase along the same phase, and quadrature 90 degree to the phase, or you can say orthogonal components. So I can write my AG theta as this XC and XJ. All right. Acha. All right. The time is up. I won't go any further. The rest of this thing is also very simple. You can read it by yourself. Otherwise, if you want, I will just revise it or just cover it in small steps, and we will be ended with this lecture in the next lecture. All right. So whatever is feasible. So at this point, I am just trying to go slowly so that we have, if you still have any questions, you can very well ask now. ये पता नहीं आप लोगों की अटेंडेंस क्यों नहीं आती इसमें, मतलब वो जो I will download the attendance list. I will end the recording so you have no questions.